The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next speaker is Desmond Bull, who is Technical Director at Holmes Consulting Group at Christchurch, New Zealand. He is also Horseum Adjunct Professor at the University of Canterbury. He is also past President of the New Zealand Concrete Society, and so on. With that, I would like to introduce Des for his presentation.
Good afternoon, ladies and gentlemen. As per, I'm also an academic in another part of my life. I've got far too many slides, so let's just see how we can go through these. I'll go back to the first slide. I originally wrote the abstract some weeks, if not months ago, for this presentation. Then Pete Barlow reminded me that it was actually for repairs, so the abstract and the proceedings has got nothing to do with the presentation today. So we're going to talk about, I've changed my mind, we're going to talk about some issues from the Christchurch earthquake relating to immediate and long-term repairs. For those who do not know, New Zealand is three islands in the South Pacific, about the land area of the United Kingdom. And Christchurch is down there where the red arrow is, and the bump on the side is actually a very old volcano. This is New Brighton Pier, one of our piers going into the ocean, obviously. This is the abutment end of that pier. Needless to say, the people on the pier needed to change their underwear afterwards. That was in the February earthquake. We've gone through an unprecedented suite of earthquakes. We're all trained as engineers to believe we have one large earthquake and then the earthquake subsides. Well, the big one was, as you've heard already, was in an earlier session, was 7.1, about 30 kilometres away from the central business district. It was a rolling earthquake. And then we had a 5.1 immediately under the city. It was a very different earthquake, short, sharp, and very, very nasty. Massive accelerations, both horizontal and vertical. But the durations are very short. And we had a subsequent suite of them. I've been through all of these, but the last one. And when you're within 5 kilometres of a 6 going up under your feet at 5 kilometres deep, it's quite a ride. And in Christchurch, we had some significant vertical accelerations in places up to 2G vertically. And again, we still haven't finished. As recently as the 23rd of December just gone, we had another couple of large earthquakes. I happened to be out of the city at the time, thank goodness. And as we all know, the behaviour of a building, the effect of a site, is dependent not only on the magnitude and depth and proximity to the earthquake and the soil type. We had a lot of liquefaction and settlement in Christchurch, but also obviously the duration. Just response spectra from the September earthquake. The black line is our then current code spectra, and as you can see, it equalled or exceeded the design code of the day. The interesting thing is the bump at 2.5 seconds. This has been known about for about 30 years. But our equivalent to USGS in New Zealand basically ignored the reports that have been around for 30 years and gave us a nice smooth line. One of our big problems is that our only base isolated structure in the South Island happens to have a response first fundamental period around about 2.5 seconds. The reason it didn't get into too much trouble was because the earthquake wasn't long enough to get the large base isolated hospital up into the resonance mode. This is a response spectra from the big earthquake, the Christchurch earthquake, where we lost 185 people. As you can see, the spectral acceleration was over 3G in the short period structures. Needless to say, unreinforced masonry buildings didn't have a show of surviving. Some of the issues related to repairs, concrete strength. It was far higher than expected, and I'll allude to that in a moment and why that might be an issue for all of us, including the code writers. Residual plastic capacity of bars and structural steel. This is not a problem related just to reinforced concrete, but it's also a problem for structural steel. How much plastic capacity, deformation capacity in that member or bar is left after a major shake, let alone a series of shakes. And of course, the big one is floor plates and diaphragms. Are they repairable? Have we lost the load paths in the existing structure, and or can we reinstate them? And the effect of elongation in the plastic hinge zones of beams. Concrete strength. The concrete strength we are seeing in structures is obviously higher than the lab concrete that we've used to develop our engineering equations and recommendations. For a start, a supplier of concrete will be targeting about 20% higher than the engineers specifying. Age enhancement of strength is about 1.5 times the strength. You'll find that under dynamic loading, the concrete, particularly the tensile capacity, can be 1.2 to 1.4 times larger. That means that the compressive strength can be anything from 2 to 2.5 times. The implications are the minimum longitudinal requirements in our standards sufficient for the real crete as against the lab crete that we're dealing with in our labs and the equations are quantified against? As a general rule, we spec the minimum steel contents, particularly in walls and some beams, were not enough to start with. And then if you add in the fact that the concrete, the tensile capacity of the concrete is significantly larger, you find that we do not have enough reinforcement longitudinal to form a distributed crack pattern, spread the plasticity. And any crack, might be one or two cracks opens up, and that plasticity is confined to a short length of bar. And here's a couple of case studies. What we're expecting from all of our studies and from good, well-detailed walls in the field is a spread fan pattern of cracking, flexure-shear cracks, which distributes the stretch of the rebar up a reasonable height of the wall. What we are actually getting and have seen in numerous buildings, I've personally seen 4, I know of at least another 5 in Christchurch, where the walls, though they're designed for flexural yielding, actually only split at one crack, typically the construction joint above the beam or the foundation. And all the bar stretch was concentrated to that one crack. Here's a situation. This is a 2005 building, a very expensive condominium apartments. The tall building on the left is the one we're talking about. The squatter building on the right is actually our emergency operations centre right next to this building. And about day 3, I got a phone call from Professor Andrew Buchanan at the University of Canterbury saying, we've got something funny here. We've only got one crack at the base of the wall. Now that means 2 things. Either the walls did not get loaded or something really bizarre happened. And so I was there and I asked for a team to come in. This is an Australian urban search and rescue team were available. They came in with their gear and started hacking away the walls for us. By this stage I had about 5 other engineers standing there. We got into this area here, and that's the blow-up of that shot. And one of the engineers said to me, that's a really funny-looking lap. If you'll notice that the bars are actually coned, and there's a nice little cup at one end. The bar's fractured. And then another engineer said, well, that's okay, it's just the bars at the end of the wall. And I said, I bet it's not. And the Aussie team came through and they hacked out all the bars along that wall and another wall and found that every single longitudinal bar in that 11-storey wall was fractured at one crack. And I know of 3 other buildings that we had a look at, we had exactly the same problem. There simply isn't enough longitudinal steel to form a distributed zone of plasticity. What we found was first impressions as the cracks meant there's no damage. I believe there's a recommendation in FEMA that if a crack in the wall is less than 5 mils, just epoxy it up. I'm not so sure that that's a good tactic to take at the moment. We have another way of dealing with this, which I'll talk about in a moment. We found that the roof, peak drifts at the roof, led to that single crack at the base of the wall opening up about 1.5 inches. And we know that these sort of bars fracture at 5/8 of an inch, so they didn't have a show of surviving. The next question is, following on from this, is what is the residual plastic capacity of our reinforcing bars in our structural steel? As I've mentioned earlier, we're not getting thousands of flexure-shear cracks. We're only getting 2, 3 or 4 cracks where all the deformation is concentrated at. The other factor is that there's very, very high localized strains in the bars either side of those small numbers of cracks. Now, from laboratory work that goes back before even we were students, you'd say under multiple inelastic cycles, you would get yield penetration, bond failure along the bars, anything from 2 to 4 bar diameters either side of the crack. This is partly to do with the loading scheme that most laboratories have used over the years, which is to progressively deform your column or your beam progressively more and more and more and more. This has led, we think, to progressive bond breakdown and a reasonable length of bar either side of a crack to distribute the plasticity. When we actually went in and measured the plasticity, we were finding that bond loss or yield penetration was about 1 to 1.5 bar diameters, not the 3 to 4 that's in the textbooks either side of the crack. So the local strain in the bars was 4 to 8 times higher than we expected. Fundamentally, so the question is, if this is actual stress strain plot from a bar we took out of a building, where are we on that curve for that bar? The question we get asked in New Zealand is, can we, for engineering assessment, which all engineers are being asked at the moment in Christchurch and anywhere in the world after an earthquake, can the building withstand aftershocks? And normally we would have said yes, generally. Is the building safe to reoccupy? Well, we don't know. Is it repairable? Well, we've found out in Christchurch, largely the answer is no. We've gone through so many large earthquakes that the cumulative ductility, the cumulative plasticity of those bars, there's virtually nothing left. And as a general rule, we're actually demolishing buildings because we can prove there's not enough plasticity left in the bars or the structural steel beams. The way we're doing this is with the Leeb Hardness test. It's a dynamic test, it's portable, it's a little device, it's calibrated. We calibrate it against the stress strain curves of the parent materials. We take bars from different parts of the structures where the bars have not been highly stressed. And this is based on AS10 standard. And we can relate those Leeb Hardness tests to where the bar is on that curve. And that makes us, then we can judge how much deformation capacity that building or that element has remaining. And we are very, very well insured in New Zealand, and unfortunately, a lot of buildings are worth more down than up. Several of the insurance policies for big buildings in Christchurch is that if you cannot return it to 100% of the now code, even not the old code, but the now code, in terms of what there has been changes and upgrades of seismic hazard, the building's basically considered to be a loss. And of course, if you've used up some of your plasticity, there's no real way you can ever return it to 100%. And that's actually been a legal argument for demolishing what is basically a repairable building. Okay, just some shots. What the technicians do is they take the cover concrete off, they do a repair of they prepare the surface of the bars we're interested in to do the Leeb Hardness test, which is a bouncing steel ball. Change the velocity is an indication on the rebound of what the hardness is. The technicians are very careful not to use heat because that changes the metallurgy. They do the preparation with light sandpaper. That's just another shot in a plastic hinge in the Price Waterhouse building, one of our second tallest concrete building in Christchurch. That's about to be demolished. Just so it's not a concrete problem alone, structural steel. Here is an eccentric brace frame, an EBF, and a parking structure of the hospital. You'll notice the paint's flaked off. This is also what happened. What the problem is that this weld here should have been there. If these were closer together, should have been welding that surface to that surface. They took a shortcut. That bent caused flexure in the flange. The flange tore and ran through the link. Just the same shot again. These zones were measured using lead hardness test and water jet cut coupons, not heat cut coupons. And found that the strains there were right at the end of what was left in those particular elements. We also found that the high strains actually worked out away and out along the header and down the legs as well. The solution was to cut those pieces out and replace them in their entirety over the building. Conventional beams in concrete, or conventional beams in general, they elongate, they get longer during cyclic loading. Concrete's the worst. Structural steel does the same thing, but to a lesser degree. And timber, where you've got hardware or steel connections, you have elongation as well. The problems are the loss of floor support and a loss of load paths. So this is a beam in a lab, and somewhat dramatically, the beams actually do get longer. And in the worst cases, up to 4% of the depth of the member. So if you've got a 3-foot deep beam, 36 inches, you can get up to 2 inches worth of elongation that you do not recover. I got told by an engineer outside New Zealand about 2 months ago that this was a New Zealand problem, and the Japanese in 1983 showed that wasn't a problem anywhere else. Well, actually, I don't think you need any convincing that this is a reinforced concrete beam that could be anywhere in the world, and it's just structural mechanics. They do get longer when they go cyclic. The problem was, this is a plan view, do we push the corner columns out, like the left one, the beams elongate in these areas, the beams elongate and push the corner column out, or do when the beams elongate at that end and that end, do we actually do the beams rotate out in the horizontal plane? We actually get both. The problem is if that gap is 2 inches and you are relying on getting compression fields across your diaphragm to those corner columns, it's very unlikely that you'll be able to do that. It's also unlikely that any continuity steel from the beams to the floors are actually still intact. It probably would have ruptured. This is a shot from the University of Canterbury research in about 2000. This is 30 feet, 35 feet, 35 feet this way and 17 feet this way. It's a 1 foot deep hollow core unit with a 2.5, 3 inch reinforced topping, and it's actually lying on the floor. It fell out at 2.5% drift. This is looking down the other way. This is from underneath. This is me walking down the stairs towards that's part of the test, and then this happened. That weighs about a tonne per 10 square feet. And it hit the ground so hard that the seismographs and engineering geology on the other side of the campus picked it up as an earthquake. You have one of those fall in one building, it takes every floor below it, all the way to the basement. So that started a number of changes in New Zealand codes on supporting our precast concrete floors, which is a dominant floor system in New Zealand. 99% of the floors in commercial buildings are precast floors with topping. That led to a number of changes through 2003 to 2006 in our concrete standards. Okay, here's some case studies. Clarendon, 18-storey building in Christchurch. We're going to have a look at that corner. The beams, the red lines, the beams elongated and pushed the white column in the corner out up to a little over an inch. The floors were flange-hung T-beams. Too much information there, but essentially that silly detail ruptures and the flange folds up and out of the way. This is looking at the middle zone of the building, and that floor tear there, the yellow arrows tells you which way the floors are moving. This is looking through that crack. It's about an inch wide, and the white light at the bottom is actually looking through to the room below. The flange hung details all the flange fixings completely failed. This dropped about 1.5 inches vertically. It didn't fall down because of catenary action, which you can't design for, running at 90 degrees to the direction of the spans. The same problem. How do we get our forces into this area? One of the other problems was if you do not have supplemental beams, secondary beams tying your columns into the diaphragm, this is a plan view like you do in steel and some concrete beams, what happens to the columns? Well, that elongation starts to push the columns out of the building. We didn't have supplemental secondary beams crossing the floor. What we were seeing was the columns buckling over several floors. So the intervention was to actually put these headed beams on the outside through the precast panels over a couple of floors spread across the building. This was an immediate step in to save us, put security in this building. This was on a long-term fix. This was a fix to allow the contractors to go into the building. Concluding comments, minimum flexural steels for realistic concrete strengths are probably insufficient in most standards around the world. Residual plastic deformations in bars and structural steel means that these buildings are probably irreparable. Floor plates, elongation is a universal problem and destroys the integrity of the diaphragms. Very difficult to repair and to replace the reinforcement in the floors. Last comment is that is an as-built transfer beam in a hotel. That's how it was built. Needless to say, we had a massive Flexure-shear failure here. And we're quite embarrassed about that, but that's one of our buildings in Christchurch. Thank you very much. Excellent.